Hey, good morning, everyone. This is Kian from Energy Department, University of Science and Technology of Hanoi, and welcome to a very special class. In this day, we are faced a situation of coronavirus outbreak, so we have to conduct an online teaching and learning course. Of course, this kind of class is really like real interaction, discussion, question, and I mean the atmosphere cannot be maintained compared to real class. So the quality should be reduced, and it's so hard to take the full advantages of the course. But I'm going to try my best to deliver all the necessary messages of the course of the class to you. So before going further, I want to take a few minutes to cover a previous class with the basic wind energy and power. So in this figure, I hope you still remember the power curve of the wind turbine. So this point we have cut-in wind speed. Here we have nominal wind speed, and here the cut-out wind speed. And the meaning of the cut-in wind speed is below this speed the turbine stops. It does not produce any electricity. And it happens the same when the wind speed goes beyond the cutout speed to avoid damages to the mechanical structure of turbine. And in order to calculate the output energy of the wind turbine, the power curve is not enough. For example, at this wind speed of 15 meter per second, the power we have nominal power. But in fact, in reality, what happens if we never have a chance to have this wind speed? So in this case, we have to consider the wind speed distribution function, which is the Weibull function, that really show you the probability of the wind speed at different speed. For example, at the speed of 5 meter per second, we have almost 5%. The probability of it is 5%. So if we consider both function, the Weibull function and power curve, we can consider how much energy we can produce in 1 year. And a statistical distribution function Weibull of the wind speed can be expressed by this function. Here we have two very important parameters to remember. The first one is k, which is a shape factor that determines the shape of the curve. And another parameter is a, which is a scale factor that will be calculated based on the mean speed of the wind. So with high value of k, it means that the speeds seem to be more stable, as shown in this figure here. We compare different value of k from 1 to 3. So of course we can see, for example, with the k equal 3, the speed of the wind should be more stable. That can fall in the range between 4 and 14 meter per second, while in the case with k equal 1, we have a wide range of speed from 0 to more than 20 meter per second. And if we multiply the Weibull function with the total number of hours in 1 year, which is 8,760 hours, so we can know how many hours in 1 year that the wind have a certain speed. For example, here in this graph, if we take integral from 5 meter per second to 10 meter per second, and this area will show you the number of hours the wind in 1 year have this kind of speed. So, and another thing to notice is the power density of the wind. Here we have two different methods to calculate the power density. The first method, we say it is incorrect method, that here they only consider the average wind speed in 1 year. And this one is not correct because does not consider the probability density function of the wind speed. By the second method, here if we consider, we have the correct method that we take integral of the speed from 0 to infinity. If we use incorrect method, it is easy and quick to calculate the power density. For example, if we know in an area, if we know the average wind speed up about 5 meters per second, so we can easily and quickly have a result of power density of about 77 watt per square meters. And of course, it's not correct because the wavefront function is not considered. In case if we consider the probability function, we can have the result at 146 watt per square meter, which is almost double compared to the first case. But in fact, if we want to consider the probability density function, we have to determine the parameters k and a, which is it takes much longer time and also is more complex to determine. So in very quick analysis, of course, we can use the incorrect method to have very rough result. And this table compared to different value of the power density for different value of k. We say that is sensitivity analysis of the shape factors. Here they consider three different value of k: 1.9, 2.0, and 2.1. And so the difference in k is 5%, and from that they can have the result different of about also 5% in power density, which is not big error, but it is really acceptable. But in common practice, in calculation, they can assume the shape factor equal to if there's no specific condition in advance. So the value of k equal to is quite common, so can use that for most of the cases without any big problem. And here, one thing to consider is the question is how to classify the wind class. So in real life, is you can say the wind is so strong, so the people will think, okay, the speed of the wind is really high. For example, 20 meters per second. But in fact, the good definition of the wind class is based on the power densities, not really the wind speed. But of course, they are strongly correlated. And here they show 7 different wind classes from poor to superb. So here in the table they put two columns. The first one is power density, and the second one is average wind speed. And this one only correct for the value k equal 2. So you can say if we know the average wind speed at 10 meter, at the height of 10 meter, and the average wind speed is between 4.4 and 5.1 meter per second, and we calculate the power density between 100 and 150 square meter, and the wind is classed as marginal. And this one's only correct, only matches for the value k equal 2. And if in another cases, if the k is higher, for example, k equal 2.1, 2.2, so in that case, the power density will decrease. So it can fall in the range of, in the class of poor. So we have to be very careful when we think about the class of wind. It should be based on the another parameters to be considered is the wind shear, that explains wind speed increases with the increasing height. For example, if we know the speed of the wind at the height h1, and so it can be easily calculate the speed of the wind at the height h2, knowing the wind shear. So what is really the meaning of the wind shear? The wind shear that can be explained by the friction between the surface of the earth and the air. This friction will slow down the wind very close to the ground. So depending on the surface of the ground, for example, if it appears the building, forest, or mountain, so that obstacle to the wind, so that really increase the friction. So in those areas, the shear will increase. So in those areas, if we go higher, so the speed the wheel will increase faster. And in this table, it show you um, the different values here according to different region. For example, for the open sea, which is we can assume very smooth surface of the ocean, so the shear is quite small. The meaning of the shear small is even if it goes much higher, the speed of the wind doesn't change so much. But in the case we have very large cities with a tall building and skyscrapers, so the shear value is really high, which is almost 0.4. So in this case, um, if we go higher in the atmosphere, the speed of the wheel will increase faster. So the question for this part that I asked our student to answer in the next class is the question about the location to put the turbine. So where to locate a turbine of 50-meter length placed for the better energy year. The first is a desert with average wind speed of 5 meter per second at 10 meter. And the second case is instead of having the desert, we have forest. So the forest with average wind speed of 5 meter per second at the same height, 10 meter per second. So we have to answer this question in the next class. So, and the next part is about the wind measurement and wind resource assessment. So, why do we need to measure the wind? Because that the idea of using wind turbine is to convert the wind energy into mechanical energy that can rotate the rotor blade, and after that it will transform into electrical energy. So if we doesn't know exactly the parameters, the data of the wind, so it's too difficult to predict how much energy we can have to inject to the grid. So that's why we need very accurate wind measurement to have high accuracies of energy yield estimation. So if we have very accurate energy prediction, so we can have the very good predict of the project financial return, which is really impact and really influence the investing decision of the investor. So for the wind measurement, we have different parameters to consider. Of course, the most important thing that people usually think about is the speed of the wind, because basically if we have higher speed, we have higher wind power density, and we have higher electricity to be produced. Another important parameters can be the wind direction, the air density, the pressure, and the temperature also. So in the wind speed measurement, we have different concepts to consider. The first is the component of the wind speed, which is which includes the horizontal and the vertical. So basically, for the common type of the wind turbine, which is horizontal axis, the horizontal component will mainly produces energy, and for the vertical component, it will create a turbulence and and it actually degrades the turbine performance. So this component we don't want to have in the wind, but actually it always appears. So we have to measure exactly these two components. Another thing is a point. The measurement, the wind speed at the point are in volume because they can be like the local measurement and the overall data of the wind in the area. So in order to have these two different type parameters, we have different technique for the measurement. For the point, we have a cup, an anemometer, and in the volume we can have we can use the remote sensing devices. They're quite different in concept, in working principle that I'm going to show you later on. And the last point is we measure the wind at the times or in an interval of times. So at the time we say, okay, at 1 second, we measure the wind speed only at the local times at a very specific point of times. For an interval, we basically we measure the wind speed at different point, and after that we can simply take it. For the speed measurement, they can use anemometers. That there exist three different types. The first one is cup anemometers that they use three cups that attach to the vertical shaft, and the speed of the wheel will be proportional to the speed of the shaft. And the second type is the propeller anemometers. And this one is different from the first type. Is here the shaft is horizontal, and the working principles is quite the same. The speed of the wheel will be proportional to the speed of the shaft, and only different is the direction, horizontal or vertical of the shaft. And the third anemometers, it is sonic typed. Here, the main difference of the third one compared to the first two types is in the third case, there's no movement compared to the two others. And here they use the ultrasound wave, and they use three pairs of transducer. The transmitter will generate a sound to the receiver, and in fact, due to the wind, it will impact the process of the receiving the signal. So based on that, they can calculate the speed and also the direction of the wind. The reason to use three pairs of transducer is to measure the wind speed in three-dimensional. And in realities, in order to put the sensors for the wind measurement, they use very high tower, monopole tower, with the height is in common of 60 meters typically, and they put sensor at different heights to measure the wind at a different layer of the air. And of course, they also put another type sensor, for example, temperature, barometric to measure the pressure, and also they can put the data logger and communication devices for the data connection and data processing. And one thing to remember in this type tower is the spares anemometers is usually used for two reasons. The first one is to avoid the center effect, because sometimes due to the tower, some sensors cannot receive the wind or receive the wind in the not good condition. Another reason is to maintain the continuous data in case of failure of some sensors. And the drawback of this type tower is nowadays the wind turbine is really high. So let's say if the blade has a length of about 100 meter, and we place a tolerance between the tip of the blade to the ground of about 30 meters. So the hub head should be at the height of 130 meters. So for the good energy prediction, so we have to measure the wind speed at that height. So it is impossible to use data measured by 60-meter monopole tower. So that is a drawback of this kind of tower, and this only used for the uh, 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 normal wind turbine in histories a few decades ago. In order to run the wind measurement campaign, so they have considered the cost, and they have to consider of the towers. They have to consider where to place a tower, and also consider the duration. It's important to consider the towers and also the placement, because the cost of the tower is really expensive, in around of 20k USD per tower in the course of 2009, and also the placement of the met tower should be the same place as turbine, but in fact they don't know where to put the turbine. They only know the place of turbine after knowing the distribution, knowing the map of the wind. So it's very concerned to put how many tower, because in order to increase high accuracy, they have to put the sensor everywhere, but it's very costly. And about the duration for the measurement, at least for for typical wind project, they need to have the wind data for 1 year at least. And to increase accuracy, to reduce the risk, the financial risk, they should increase the measurement period to 3 or even 4 years. But should be more costly, and it will make the project longer before. So we've just talked about the wind measurement technique using an anemometer that only measures wind at a point. And in order to deal with the drawback of an anemometer, which is the problem of pretty low tower, which is about 60-meter tower, that cannot be used for the very high to be nowadays. So that's the reason they will use remote sensing, which is considered a very advanced technique. This technique uses droplet effect, which is a change in frequency of a wave in a relation to an observer, which is moving relative to the wave source. So there are two different techniques they can use. The first one, they use sonic detecting and ranging, which is solar, and the other one is light detection and ranging, LIDAR. And they are working in the same principle, and of course the difference is based on how they generate a signal. The first one, they create a sound. The second one, they create a light. So by this technique, they will measure the wind in a very large the volume. So after that, they can take an average, and of course it cannot be used for determining the local information of the wind. But the main there are several advantages and also disadvantages of this technique. The good one is they can measure the wind for very high turbine nowadays, which is can be in order of 200 meters. And second advantage is mobility and very easy to deploy, especially for offshore wind management, because in the offshore wind is too difficult to use so many tower for the anemometer technique, and also it's quite easy to repair. But the problem is it can be influenced by noise for the solder, and also experience is required to um, to filter the noise from the signal. And the second disadvantage is it only considers the data is very large volume, so it will reduce accuracies for the certain turbines. And the last one is the solder, because it creates a sound, so it can make the environment noisy. And here we move to the wind resource assessment. And here's I show a very graph about the assessment of the wind resources. The first one, we need to carry out the preliminary assessment that it should the first one, we need to carry out the preliminary assessment that will use all the possible available sources of wind data. For example, from the USA National Climatic Data Center, so they will provide very well-controlled data for the wind turbine. And in this step, they also involve the financial evaluation of the project. If it is acceptable, they can go to this next step, which is on-site measurement. And these steps, they can use so many sensors to measure the data for the wind in a long period of time. I mean, at least 1 year for the normal project, or 2 or 3 years for the big project, to reduce the financial risk. And after having all the possible data, they will do the spatial extrapolation, because they cannot have so many sensors at all the points. So they can put sensor at certain points, and after that, for the whole space, they need to do the spatial extrapolation. And after having all the data available, they will calculate the annual energy production for all the turbines of the wind farm, and uncertainty analysis will be carried out also. And for this one, the final step is to do the financial analysis, which is really determine if the project is worth investing or not. And for the here I show you here I show you different type of losses for the wind farm that should be very important to determine the wind energies. The first one, to wake loss, which is in order of between 5 and 15% of the total loss. And the meaning of wake loss is, okay, in the wind farm, normally the turbine is put in a round column. So basically, the first round will receive all the wind in normal condition. After the wind passes the first round, it will reduce speed and also create the turbulence. The reduced speed and turbulence will strongly impact the turbine in second rounds. I mean, the second round will not perform at 100% as its first round. So this one will create a losses in its next round. The second loss category is the plant availabilities, and the losses for this time should be from 2 and 5%. The first one can be problem for the turbine maintenance, and also the failure of grid can be also big trouble. If we have to maintain and make some repair for the turbine, so the turbine has to stop and no electricity is produced. And same problem for the failure of the grid. So in that case, the wind farm has to be disconnected from the grid. So even though there's no problem with the wind turbine, so all the energy can be coming out, but it cannot go to grid. So there's no connection, no electricity available to the grid. The next type is the electrical losses, which is in order of few percent, 2 and 4% of the total losses. These losses are associated with the losses in the generators, transformers, and also the transmission losses to the grid, because between the wind farm and the grid we have a high voltage cable. So this one we have losses, and also the wind farm internal power consumption, because in order to run a wind farm, some component inside the wind farm will consume directly the electricity produced by the wind farm. I mean, all the energy should not go to the grid. A part of that will be consumed locally. And next losses is the turbine performance, because all the turbine should not and cannot perform at the ideal performance. For example, the power co-loss due to the deterioration of the blades and gearbox, etc. And also another factor is high wind hysteresis due to the poor recovery from shutdown due to the high wind speed. For example, if you still remember the meaning of the cutout speed, if the wind speed goes beyond that speed, the turbine should stop. And now the speed of the wind decreases below the cutout speed, and in theory, this turbine should be recovered back to the normal operation, but in fact, it's not. It can go below a certain level, and we will start again. So that kind of losses compared to theory, they call it as high wind hysteresis. Another losses to be considered is the wind modeling, because in theory, even in simulation, some type of very small loss is not considered, and because it's too difficult to model. For example, the inflow angle and the rough terrain for the real condition. Another factor to be considered is environment. For example, the icing, an earthquake, and extreme condition. In these conditions, the turbine cannot perform, cannot operate, and it has to stop. And also another factor is lightning strike, and because in the storm, we have the lightning directly strike to the turbine and can create damages, and the turbine has to stop. Another factor is rough leaf changes. New forest, new building is built, appears in reality. For example, when we start the wind project, everything's okay. There's no big forest, there's no big building. So after a few years, after a decade, the building appears and it will reduce the wind speed. So when the wind speed reduces, the output energy will reduce. And also the last factor to consider for the energy loss is the grid operation. For example, the energy demand and dispatch. The energy demand is in case the demand of energy is lower, so the wind farm cannot produce the nominal energies as designed. And also in dispatch, it is the same situation. From the operator, they can decide how many energy, how many power should come from the wind farm, how many power should come from the hydroelectric power or nuclear power. So that will change, that will impact the total energy produced by the wind farms. So all kind of losses will contribute to the reduction of energy production compared to the one calculated in theory. So that will actually increase the energy cost. So we have to consider that very carefully in designing. And recently we have the failure of 1.5 megawatt wind turbine in Bintang plant in January 2020. That it's it, to my knowledge, it is the first failure of the wind turbine in Vietnam, but it happens quite a lot in the world in histories. And this kind of trouble, the first, it will create the reduction of energy because the turbine has to stop. Second, it will cost some money for the maintenance and repair of the bullet of the turbine, and also the old component inside the nacelle. Okay, thank you for this class. Thank you for your attentions. I hope I gave you very general, brief, the key point of the lesson, and please remember to do this exercise before the next class. And if you have any question, please email me directly or contact me for further explanation. So see you in the next class.